think we'll give everyone just one more minute to show up and then we'll get started. All right, let's go ahead and kick things off. So first of all, welcome everyone, and thank you so much for coming to another one of our webinars. I really hope you guys find this informative and are able to make use of this information. So this webinar is on solder paste powder size and trying to give you guys some guidelines on when you need to downsize your paste. So my name is Gail Towle, and I'm your speaker today. I'm a content specialist at Ames Solder. I'm background in math and physics. I used to teach college students, did a lot of writing and creative writing over the years, and now I write for Ames Solder, and I work with a lot of technical content and try to become an expert on everything I can so I can inform our customers and inform our internal people as much as possible. So to start off, we're going to just do a little overview of solder paste basics. A lot of this may be very familiar to some of you, but it gives us sort of a starting point to launch into a discussion of powder sizes. So solder paste, as you likely know, it's made from a combination of solder powder, which is very tiny spheres of alloyed metal. And they are, the goal anyway, is that they are as close to spherical as possible. So they're not just little scrappy bits. We try to make them spherical for a few reasons. One is they work better in the paste, and the other is that minimizes how much surface area they have, which can reduce oxidation, which is a really big problem with solder paste. The other component is the flux medium. So that's the goo that holds it all together. It also acts as an activator to help clean the metals and the surface and make everything bond together nicely in the reflow oven. So solder pastes are classified based on the size range of the little powder particles they contain. Those particles can range in size from type 1 to type 10, although you almost never hear of type 1 or type 10. Types 3 to 6 are currently the most commonly used in electronics manufacturing. Right now, type 4 is the most popular paste. The particle sizes in type 4 powder range from 20 to 38 microns, and it can print down to O201s and micro BGAs. In this next slide, we have sort of a really good visual of how these different particle ranges compare to each other. So this table on the right shows you type 1 to type 10 and the smallest and largest sphere diameters for those powder size ranges. And these spheres are all to scale, so the relative sizes are somewhat accurate here. And so you can see, type 1 that again isn't really a thing anymore. Type 3 is getting pretty small. Type 4 is even smaller. That's our most common. Type 5, we're going to discuss quite a bit today. Type 6, you're getting even tinier. Then you start getting to 7, 8, 9, and so on. You're getting very, very small. I always like to give people a reference to sorry, someone just tried to take control of the presentation. So All right, so I like to give people a reference to understand how big these things are. And so if you can imagine white blood cells are about the size that sits between type 6 and type 5 solder powders. Very, very tiny. Another good reference point, so the diameter of a human hair, that's about 100 microns on average. And so if you're looking at type 4 powders, you're about a third that size in diameter. So in the early 2000s, type 3 was the standard. It was very broadly used in electronics manufacturing. But as components started shrinking, so did these solder paste. So as 0402s and 0201 components started to become more standard, the industry shifted to type 4. So miniaturization, of course, is the one biggest drivers. You have tighter process control required. You might have high input output devices that you need to print. And so that uh, pushes people to go to smaller sizes. So type 4 is the current standard. Type 3 is still used, but it's not as common, and it's definitely been phased out in a lot of precision applications. So tighter pad spacing, really small print apertures, finer pitch components, all of those require smaller powder sizes. Anyone who's using jetting or micro dispensing applications, often those require finer powders like type 5 and smaller. When designs start getting down to those 01005 components, and you'll hear me talk a little bit more about that later, that's sort of where that crossover happens, where you need to move on from type 4 in most cases and start working with type 5 or even smaller pastes. So currently what we see, the number of type 5 users is small, but we're expecting that to grow. And again, part of the goal of this webinar is to really give you guys some guidance around when you need to make that shift, what you're going to need to consider when making the shift to smaller powders. And so you're fully prepared to know what questions to ask and what to be thinking about as you get to that critical point. So what's driving the shift towards this miniaturization is many, many different sectors, but primarily we're seeing it in automotive electronics, medical devices and wearables, things like that, often have to be very small. And advanced displays, micro mini LED, we're seeing an awful lot of type 6 applications in that space as well. So when do you need to consider a smaller powder size? So first, there's several things you need to think about in your production process. You need to know what your smallest stencil aperture is that you're printing through. That's usually in conjunction with what's your smallest component that you're printing. And then you also need to think about how good your process control is and whether you're having problems with stencil release or inconsistent deposits on your smallest print pads you're printing on. So one metric people use to try to determine when to go smaller is the so-called 5-ball rule. And really this 5-ball rule should be called the 5-ball suggestion. It's not a hard and fast rule by any means, but it gives you a good sort of rule of thumb for when to be thinking about the next size down. And this rule essentially states that the smallest stencil aperture should be able to fit at least 5 times the diameter of the largest solder particle within the paste. So if you're working with type 4 paste and the particle range there is 20 to 38 microns, you take that 38, you multiply by 5, you get 190. So if your smallest diameter is 190 microns, that's about the smallest you can successfully print with type 4. For type 5, which the particle size ranges from 15 to 25 microns, you take the 25 and multiply by 5, and that gets you down to 125. With type 6, similarly, largest particle size of 15 gets you down to apertures of 75 microns. But again, that's not a hard and fast rule. Sometimes you can get right down to that limit or even beyond it if you have really tight process control. In other cases, you may need to be downsizing your paste before you get to that limit. So this table sort of gives a rough guideline of what's the smallest aperture based on the 5-ball rule, but then also sort of what's a range of, if you don't have very tight process control, really good release on your stencils, what might be more realistic. So when to downsize, the table on the right shows for type 4, 5, and 6 powders, just a rough idea of what types of things you can print with those. But the general rule is to always use the largest paste size you can get away with. So if you don't have to downsize, don't. And that's because there are trade-offs when you go to smaller powder sizes, and we'll be talking about those in a little bit. So yeah, so I mean, the price can go up, the ease of use can go down, and your process control and the equipment you use may need to be adjusted as well. So just as an example, we'll take 01005 components as a border case. So these components measure 400 by 200 microns. The IPC recommends stencil apertures be 175 by 250 microns for these. And this is outside of what type 4 should be able to print, right? So type 4, you could supposedly get down to 190 microns based on the 5-ball rule, and that 175 is below that. But you can make adjustments. It's possible to use a rounded square aperture design with a side length of 190. Or slightly, or even a little bit larger than that. And then you're able to get enough solder volume in there that you can still print these components with type 4. That does require very tight process control and may not be something everyone can achieve, but it's something we have seen done. So transfer efficiency, so how much paste you're able to get to stay on the board after you print, can be improved by many, many factors. So one is if you nano coat your stencil, that helps with paste release. And there's other things I've seen as well. There's even like ultrasonic squeegees that sort of vibrate as they move across the paste, which helps sort of get that paste down into the aperture and helps it release better from the stencil. So a summary of our current guidance on when to downsize is, first, always use the largest powder size that works with what you have. The 5-ball rule should be considered, but it's not the only factor. Again, it's a rough guideline, and you may be able to get to that limit. You may be able to get beyond the limit, or you may not be able to get to that limit with your current paste. So it's just, again, a very rough guideline. Paste quality is a big factor. Process control is a big factor. So if you have a paste that isn't releasing well from the stencil, or the paste medium isn't a very good one, then it's going to be harder to print smaller apertures with larger powder sizes. If your process isn't very tightly controlled, you may struggle getting enough paste release with larger paste sizes, but you also may encounter other struggles when you downsize in paste that could make the trade-off worse in that direction. So we generally suggest downsizing from type 4 to type 5 if you're going any smaller than 01005s, or if you can't get successful print transfer when those are your smallest components. Downsize to type 6 if you start going any smaller than 125 micron stencil apertures, or again, if you can't get successful print transfer with type 5. So now we're going to talk a little bit about the pros and cons, some of the trade-offs when you start downsizing your paste. So the pros are you can print finer features, you can get better print transfer with smaller apertures, and you can have less variation in your print volume. So again, you can print those smaller items, but there's trade-offs. So the cons are you may need tighter process control, particularly when you're getting to type 6 pastes and beyond. There's a higher risk of oxidation, which we'll discuss in more detail in a moment. There's an increased risk of certain defects, and in some cases, because you have to meet that tighter process control, you may need to upgrade some of your equipment. And then, of course, there's an increase in price. It's harder to create the smaller powders and the finer pastes, so the price goes up accordingly. doesn't want to move forward. Hold on a moment. Oh, we jumped 2 slides. All right, so oxidation. Oxidation is when you get that buildup of oxides on the surface of a metal. And you don't want that in your solder joint. The flux medium is designed to sort of clean off that oxide, but it can only do so much, right? So that happens on the surface of a metal. And when you have all these little tiny metal spheres, the smaller those spheres, the more surface area you get. And the way the math works out is as follows. Suppose you have a sphere with diameter d. If you take that sphere, that same amount of material, and you break it into smaller spheres, and you want to make those spheres half the diameter. Using the same total mass, you'll get 8 such smaller spheres. And if you compute the surface area of that large sphere compared to the total surface area of those 8 smaller spheres, you have twice the surface area in those 8 smaller spheres. So when you cut the diameter in half of your spheres, you might, for the same total volume, same total mass of your alloy, you have twice as much surface area exposed to the environment. And so you have essentially twice as much opportunity for oxidation. And so that's the rule to remember. Every time your sphere diameter cuts in half, you double your surface area. And this graph shows just how much that really scales as you go to those finer and finer powder sizes. So on the x-axis, we have the average sphere diameter or the median sphere diameter for each of these particle ranges, type 4, type 5, and so on. So as we go from right to left, we're going smaller sphere size. And then the y-axis is basically the relative amount of surface area, right? So for the same amount of mass or material, how much relative surface area do we have? And so as we go from type 4 to type 5, the amount of surface area goes up. 5 to 6, it's going up by quite a bit more. And as we start getting very, very small powders, it shoots up a lot. Okay, so there's a few things that happen. One is the flux mediums often get modified. So you'll often see, and we offer different flux mediums for our type 6 and beyond, because you have to mitigate that oxidation better. Another thing that happens is oftentimes you'll need to implement nitrogen during the reflow process because nitrogen displaces the oxygen, which causes the oxidation. And so you have the nitrogen there, and that helps minimize how much oxidation can happen, which type 5 is not necessarily needed, but once you hit type 6 and smaller, it's essentially mandatory that you use nitrogen in your reflow. Here's just an idea of how these different particle size ranges compare so that you understand how much of a trade-off there might be as you go down from one size to another. And so along the bottom here, we have essentially the diameter going from 0 to 45 microns. Type 3 is up top. Let me see if I can do a pointer. Maybe not. I don't know if people can see my cursor or not, but type 3 is up at the top here, and you can see its particle size range is fairly broad. Type 4 overlaps quite a bit with type 3, so there's not a lot of trade-off going from type 3 to type 4, right? You're just getting some finer powders and you're eliminating some of the larger particles. Type 4 to type 5, there's still quite a bit of overlap, although it's only about half of type 5 is subsumed by type 4. So there is a little bit of trade-off there in that jump. The biggest jump happens if you will shift from type 5 to type 6. For whatever reason, those who determined what these ranges should be did not have any overlap here. So type 5 to type 6 and smaller, that jump, you're sort of transitioning to a whole nother beast. So the type of process control and mediation techniques that need to be implemented once you jump from type 5 to type 6 is a much bigger jump than going type 3 to type 4 to type 5. So that's something to keep in mind. So now we're going to talk a little bit about process control requirements for these finer pastes. So a couple of things to note. So when you're working with finer pastes, common defects become more important to minimize because of precision requirements, but also more difficult to mitigate because of the size, spacing, and the number of components. So the double whammy, it's more important that you get rid of all those defects, but they're also harder to mitigate because of how much you have going on the board. So if you're moving from type 4 to type 5, again, that's not as much of a shift as the type 5 to type 6 and beyond. But you may use somewhat thinner stencils depending upon where you're at right now. One thing to keep in mind, and this is true with any downsizing, if you go from type 4 to type 5, you're going to improve your transfer efficiency. But you're going to improve that transfer efficiency not just on those smallest apertures that you were aiming to fix, but on all of your apertures. And this can cause more solder to end up on the board on those other pads. It can lead to defects like solder balling. So you may need to adjust your stencil in its entirety, reducing the aperture volumes of some of your larger apertures by 10% or more to sort of compensate for that increased paste release. Finer particles also are more likely to slip out from under the stencil when you're printing. And so making sure you have proper gasketing, that stencil is making very good contact with those pads on the board is also important. So once you hit type 6 and smaller, things become a lot trickier in this region. So even tiny variations in the thickness of the solder mask, the thickness of the board, or coplanarity, so it's being nice and flat, that can lead to big problems. In this realm, a 10 micron variation can change solder volume by more than 30%. A lot of times we see stencil thicknesses of 30 microns are thinner, so we're getting down to that 1 mil stencil thickness range. Another thing we've discovered is area ratios might need to be larger than 0.66, especially if there's a solder mask. And as to why this is actually something I've been playing with the mathematics behind. And I think the area ratio rule isn't scaling with volume, it's scaling with area dimensions. And when we're shrinking in volume, that sort of wasn't taken into account. So possibly in the next year or so, I might have a paper out showing the math behind it and giving some clearer guidelines on what those area ratios should be for different stencil thicknesses. Stencil coatings. So again, coating your stencil, nano coatings can improve transfer efficiency. But the other thing to keep in mind is if you're putting a coating, you might end up with variations in thickness. And so you have to make sure those stencil coatings are nice and uniform so you don't end up having other problems associated with that. Other things you can do are modify the aperture slightly. So if you are trying to fit a certain volume of paste in a certain space, while getting good release. So a circle, you don't have any corners. Oftentimes people think of a circle as having better paste release because of that. I'm not sure if that's always the case. But fitting a circle into a certain diameter area or certain sized area, you can't get as much volume. If you make a square aperture, you can get more volume in that same space. However, now you have corners and stuff likes to stick in the corners. So the compromise between those two is the so-called squircle aperture, basically a square with rounded corners. And that helps maximize volume in a tight space while also improving paste release. So things to consider, other process adjustments are the squeegee and the print settings. So the speed, pressure, and other variables of your squeegee may need to be established by experiment. So we can't always just give you the numbers to go on right away. Different processes are going to work differently. And so you may need to fine tune those parameters to see what works best. The other thing is you may need some tooling to help. So again, remember that coplanarity, keeping that board very, very flat, is key in getting a really good print, especially when things are very, very tiny. And sometimes the substrates are thinner in these cases as well. So you may need to have something underneath the board to support it and to help it maintain that flatness during the printing process. Other things you may need to consider, equipment upgrades. So your pick and place machines need to be even more accurate. Again, if you're working with tinier components and tighter spaces, that margin of error needs to also be smaller. And so there may need to be an upgrade in your pick and place machine or whatever method you're using for placing components. Solder paste inspection is another one. If your current equipment can't give you the resolution you need to measure those tiny deposits, you may need to upgrade that as well. So that's, again, especially the case when you're getting down to the type 6 and finer powders. Reflow profile adjustments. So nitrogen is one of the biggest things that changes. Type 5, it's not necessarily needed, but type 6 and smaller, we generally tell people it's mandatory at this scale. So being able to have nitrogen in your reflow oven is important. Because these components can be very tiny and very light, think about a water skipper on a pond, right? It sort of glides across the surface of the water. That's what these components can do. That surface tension of the melted solder may cause them to sort of shift around or slide around on top. And so that's another thing you have to consider. So minimizing the amount of vibration or motion that happens after those components are placed and after the solder is melted before it solidifies. So reflow profiles may need to be shorter. That's not always the case. This also depends on the thermal mass of the board and the components. For type 6 and smaller, sometimes a short 3-minute ramp to spike profile is what's recommended. But again, that can vary depending upon the board and what is on it. Storage and handling of solder. So because finer powders are more prone to oxidation, the shelf life starts getting shorter. So we always recommend storing our solder paste under refrigeration, although they do have a room temperature shelf life as well. But the longer you can keep something refrigerated in these cases, the better. And then limiting exposure to air when possible will also help maintain the performance. So now I want to just go through some case studies. So these are just examples we've seen of people using type 5 and finer powders and what they experienced and what some of their process parameters were. So these first few are type 5 examples. So we had our M8 SAC 305 type 5 solder paste. It performed very well and was adopted for mass production in a consumer electronics application. In this application, the stencil was 100 microns thick. The finest pitched was 150 microns. The most challenging feature to print was a micro BGA, and no nitrogen was used in reflow. In another example, our halogen-free H10 SAC 305, Type 5, and Type 4 were compared head-to-head. Type 5 did outperform Type 4 for paste release on the smallest pads, but it still had good release with Type 4. So this is an example where if you didn't want to go smaller, you didn't have to go smaller. So the stencil thickness was 100 microns. Smallest apertures were 150 by 210 microns, and then a 250 micron round aperture. So again, that 150, that's below that 190 5-ball rule minimum for Type 4. And this was, again, without nitrogen reflow. So Type 5 worked better, but in this case, they still were able to make things work with Type 4 if they wanted to stick with that. H10 Rel 22, that's our high reliability alloy with the halogen-free paste. Type 5, it outperformed a competitor SAC 305 Type 5 in an automotive application. Here we had a stencil thickness of about 3 mils. Finest pitch was 180 microns. Most challenging feature was a micro BGA, and in this case, they did use nitrogen reflow. Here we have a water-soluble, our W20 SAC 305 Type 5, and it outperformed a competitor SAC 305 Type 5 in a computing application. Again, we had a 3 mil stencil. Finest pitch was just below 130 microns, and the most challenging feature was an 01005, and they used nitrogen reflow in this case. Now we have some Type 6 applications. So our Type 6 paste is our NC259 FPA for Type 6 and finer powders, and it is no clean and halogen free. This SAC 305 Type 6 performed well in a telecom application. The stencil thickness was 38 microns, so about 1.5 mils. The finest pitch was 130 microns. Smallest feature was an 008004, and nitrogen reflow was used. Same paste medium with our high reliability REL 22 alloy. Had excellent voiding and printing results on a mini LED application. Stencil thickness was only 25 microns, so about 1 mil. And finest pitch was 130, and then it was printing mini LEDs. And again, Type 6 nitrogen reflow is used. We had an SN100C Type 6 application, and it performed well on a beta site project. Again, we had that 1 mil stencil, below 130 micron pitch, and it was printing mini LEDs and using nitrogen and reflow. And then we also have a Type 7 application, and it provided good wetting in an LED situation. Similar stencil thickness and pitch with mini LEDs. 80 micron diameter circle apertures were printed with this one. So that's just some examples of how these pastes are being used and what those parameters are. So now I'm just going to give you a little overview of what our product offerings are in this space. So Type 5 right now is readily available with our H10, that's our no clean halogen free medium, and our M8, also a no clean medium, and our W20, that's our water soluble paste medium. So those mediums, and then our SAC 305, and then REL 61 alloys. So it's really easy to get samples for those. We do offer them in other alloys and other combinations, but for those you'll need to have a discussion with your salesperson or another representative at AIM. Type 6 and Type 7 offerings are available with our NC259 FPA paste. That's a no clean paste. SAC 305 and SN100C alloys. We also have jetting pastes. Our J8 is in SAC 305 Type 6. We offer a paste specific for micronic jet printers in SAC 305 Type 5. And then again, we do have other Type 5, Type 6, and Type 7 pastes available upon request. So depending upon your application, we can discuss that with you to see if we can get you what you need. So these paste mediums, H10, again, this would be Type 4 and Type 5 pastes. This is halogen-free, no clean, and it has been performing very well, passes all the basic tests and so on. M8 is also a no clean. This one is not halogen-free, so it's a little higher activity paste, but this one's been performing very well in many applications. It tends to minimize a lot of defects. And again, available with Type 4 and Type 5 pastes. We have our most popular water soluble is our W20, and it's halogen free or zero halide, and you can get Type 4 and Type 5 pastes with that as well in SAC 305. And then we have for Type 6 and finer pastes, we have an ultrafine, no clean, halogen-free NC259 FPA paste, and that's been performing very well. This one was released, I think just last year in the market. And this is some of our alloys. So our REL 61 alloy, if you came to our last webinar, we talked all about this one. This one we're very proud of because the beauty of this alloy is it works as a replacement for SAC 305 that tends to be lower cost. Depending upon the highly fluctuating metals market, that lower cost can be 10% up to even 40% because it has lower silver than SAC 305. Now, usually when you go to your lower cost, low silver alloy, there's performance trade-offs. But the beauty of REL 61 is that it actually tends to perform better than SAC 305 in a lot of applications. It drosses less. On the right, you see this picture of grain structure. After thermal aging, SAC 305 starts to develop these large-scale structures that can cause cracks, and REL 61 doesn't. It also has a slightly lower melting point and also seems to perform really well across a lot of applications. So wave soldering, SMT, but also, why am I blinking? Selective soldering, it performs very well as well, and you get really good barrel fill with it. So this is just some other product offerings we have in that ultra miniature space. We do offer some tacky flux mediums that help with mass transfer, dipping fluxes, of course, our alloys. We also do have available a sort of higher temperature tin antimony alloy that some people have been using, and underfills and epoxies as well. And then here at the end, I just have some links, and when you'll get this presentation shared as a PDF later, and you'll be able to access these. These are all on our website, just some technical articles and some blog articles around understanding solder pastes, what the different things need to be adjusted for different sizes, guidance around when to downsize, and so on. And also our declaration that 2025 is the year of Type 5 solder paste. And again, that goal with that is not to say the industry is shifting to Type 5 this year, but that we're preparing for that shift this year. We're providing everyone the information they need to know when they need to make that shift, what they need to do to make that shift. And we've got samples readily available if you would like to try out Type 5 paste as well. This is just a summary of our technical support services. We, of course, brand ourselves as not just being solder suppliers, but we are solder plus support. So we offer, of course, our robust technical support people who are all over the world ready to help you whenever you need it. But we can do solder joint analysis, stencil design support, solder pod analysis. We have a really good reclaim services program where we can recycle your spent dross and give you some money back on whatever we can, whatever metal we can get out of that. And then consulting and technical training is available as well. This is our sort of promotional why we're so awesome, the AIM solder difference. Again, we've been around a long time. We are global, and in the current interesting global market, we have manufacturing located in Canada, in Mexico, in Asia, in various locations around the world, and we can ship from different locations. So we're able to handle some of those trade issues better than many other companies. So that's another thing worth noting. We had a really good R&D program, lots of innovation happening, and our goal is quality. We want to make a good product that you guys can use and support you in the use of those products. And that brings us to the Q&A session. So I'll open it up if anyone has any questions. There's over 100 of you here, and you're all so silent.
I have a question.
Go ahead.
You talked about shelf life when you're talking about T4 versus T5. It's going to vary, I'm sure, but is there a general trend that you would identify? I mean, 6 months to 5 months, or 6 to 5.5, 6 to 3? What do you think?
We've currently been quoting that it has roughly the same shelf life as Type 4. We might do some further studies to see if we can really give what the cutoff is. Of course, shelf life is always a rough estimate, right? I mean, it depends on storage conditions, and it's not like one day the paste is good and the next day the paste is bad. It's a slow degradation over time. Um, so right now we're quoting that they have similar or roughly the same shelf life, but that may be adjusted after we perform further studies.
If I
Yeah.
can add to that, Gail, it would be alloy, it could be alloy specific too. So different alloys are more
Yeah.
sensitive, different flux mediums are more sensitive. So for the no clean products that we're actively promoting as part of our Type 5 campaign, they are the same as Type 4. So that would be M8, H10, our water soluble pastes. We're keeping the same for now. I don't have a time machine. I can't go forward to determine if these things might get shorter, but we're keeping everything the same for now, anticipating based on previous experience that it should be fine.
Yeah.
I think Gail made the excellent point that transitioning to Type 5 from Type 4 is not a sea change. Things really get strange with T6 and beyond. And I can say that the shelf lives for T6 are considerably shorter than for T4 and 5.
No, okay, so the big jump, like you've been saying, is between 5 and 6, not necessarily 4 and 5. So I just know as an industry, we throw away a lot of paste when it hits a particular time because I think it's very rare that somebody's going to say, "Oh, it'll be fine." Most people are going to say, "No, I'm not
No, I
betting
don't.
my PhD on the fact that this is fine." If you could invent a way to figure out what's acceptable by a test, that'd be great. But I get your answer though. Thank you. So it's a fuzzy line. I get it.
Yeah.
It's a bit fuzzy, and I often that I answer that question very often because even within the stated shelf lives for these products, my guidance is always if you're printing, 0.4 millimeter BGAs, don't use the old paint. Use the fresh paint. But if you're printing bottom sides all 0603s, sure, the old paint's probably fine. You know what I mean? There is some subjectivity in that because some of these characteristics of the paste can be really difficult for us to identify in a lab setting in our shelf life tests. For example, like voiding percentages. Um, there's so many inputs that can lead to variation in voiding. All using fresh paste when voiding is a concern is always again a recommendation. But again, depends on the inventory, depends on your supply chain. There's those other things. Oh, they may not manifest themselves depending on the other materials and other aspects of the process. So fresh is always better, but not always required.
Got it. Thank you very much.
Sure.
We have a few questions in the chat. I know someone had asked if there's a similar shelf life include open paste at room temperature. And yeah, I think the answer is essentially the same there. We quote the same shelf life. There may be some variation. It's a fuzzy line. So for type 4, type 5 anyway. Type 6, it's again shorter, much shorter. And then we also have a question about, is AIM looking to go smaller with ball size? So right now we offer type 5, type 6, and in some cases type 7. We have an active research and development program on refining our processes and getting those smaller powder sizes. Tim might be able to speak to when we might see a type 8 or something of that nature.
Never.
Never. Don't
Well, I
believe him.
mean,
He's lying, guys. But it might be a while.
yeah. So as we mentioned, transitioning from type 5 to type 6 is where things get weird. This is, an ongoing product development initiative that we have internally. Fluxes that we currently manufacture that are blended with type 4 and type 5 don't work as well in type 6. And as Gail mentioned, nitrogen is mandatory for type 6. Now, there's a couple things paths that we can pursue. One path is we make fluxes that work with air with type 6 and finer materials, but there's some competing material interests there that may make that not possible. And then if nitrogen becomes a mandate, that changes our philosophy on the flux that we would develop, knowing now that nitrogen has to be used. So that could open the window for other materials and other chemicals that can be input that may or may not have been appropriate when you're trying to reflow an air. So that's the development that's ongoing. I think the consensus is generally that nitrogen will be required for type 6 and beyond. So with that, I mean, I don't know, I got 5 different chemists working on finer mesh powders. I mean, the general consensus is, for any of you guys that have been in this industry for any length of time, smaller, more functionality is always going to be the way this industry is headed. And the lines between chip scale packaging and traditional surface mount are getting a little blurrier. And we anticipate that the requirements for type 5, type 6, and beyond are going to become more common. What we're seeing is that some components that demand type 5 are now making their way into regular production. And that would be your old, as Gail mentioned, 01005s, metric 0201s, 0.3 millimeter BGAs. We're beginning to see these used more commonly in production. So that's the initiative. It's why we're having this webinar. We want to give you guys some insight as to what things you need to contemplate if you see these components being part of your assembly roadmap.
All right, so we have another question that's sort of tangentially related here. Do we offer type 3 RMA SN63 solder paste for space high reliability? I'm fairly certain that is one of our offerings.
Well, ironically, that's going in the other direction. Yeah, of course we do. But the problem is that user base is shrinking. So it's becoming somewhat, I'll use the word artisanal, in that the user base is shrinking. So it's a matter of production scale. It's readily available, but with fewer and fewer users, higher minimum order quantities and higher production runs that I have to do in order to make a batch. Those might be some of the supply chain issues that you could encounter in using these, what I would consider to be legacy products. But they're around. They're not going away. And sometimes it's more cost effective to continue to use a low runner than it is to attempt to qualify a new product, which can be hundreds of thousands of dollars depending upon the industry.
All right, any other questions from anyone? Let's see, can you recommend a preferred flux type for processing in a high environmental temperature? So I'm wondering if you mean processing, if the like a high reflow temperature, or is the after it's reflowed and the product is out in the field, we're in a high temperature? Room temperature. I'm not sure a preferred flux type for processing in room temperature. I guess I'm not quite understanding this question.
Don't either, Gail. It's either they're in a high operating environment or in a high temperature processing environment, or looking for a high temp alloy. It's unclear to me. So
yeah, I mean, we do have a soon to be released flux and alloy combination that are meant for higher temp reflow. So that's a tin antimony SN95 SB5. So I don't know if that's the question, or if we're asking about high reliability alloys. We have that REL 22 that can handle thermal cycling and things like that very well as well. So I'm not sure if that answers your question, but definitely feel free to clarify if we missed it. Anything else?
Oh, maybe not directly about pastes. No clean fluxes. When we are going to apply conformal coating on board after soldering, is it necessary to clean or we can left flux on board?
So that depends. You can.
That's a
So
great
we've
question, Gail. If
done.
you don't mind me
You go
interjecting
ahead.
on
Go
this one,
ahead.
I
You
have a
were
lot of
there with the study.
experience with this one. Yeah. So it's a great question. And if you read the application instructions from the conformal coat manufacturer, they'll typically say something along the lines of the surface should be free of all dirt, dust, oils, etc. before applying the coating. Having said that, they will also say that 95% of the product we sell is applied over no clean flux residue, in direct violation of their recommendations. But the cleaning process is expensive, time consuming, all of the reasons that we don't want to clean. So in high volume applications, specifically automotive, where conformal coat is commonly used, most of it is applied over no clean flux residue. Despite the conformal coat manufacturer's statement, which is really to CYA in case something goes wrong. It's incumbent upon the whether the assembler or the OEM that is specifying the material sets to verify that there are no compatibility issues between the two materials. We conducted a study. We have a paper on our website, or we will soon, or it can be sent to the group who is ever interested. But basically the industry, there is no industry standard. So IPC doesn't say if your two materials go through this test and they pass, that's a pass. They are working on developing that standard. I know Gail and I were at Apex and we spoke to Jason Keeping, who's running the coding task force, I think is what it is, to come up with that standard. But generally speaking, surface insulation resistance is the accepted test when the two materials are in combination. And in our studies, we did see a marked difference between the different materials that were used, between the flux residue and the coating. So whether it was an acrylic, whether it was urethane, whether it was a silicone, whether it was an acrylated urethane, there were different results. So the answer is, Gail is right, it depends, but there are generally accepted methods that are used in the industry to establish compatibility, but there is nothing official. So you need to work with your customer or your engineering department and come up with the protocols that give you the information that you need to know that the material sets you've chosen are compatible. Is that a good answer?
So in other words, it's
you.
better to test.
Yeah, and rely
try
on your
to
vendors.
apply and see how it works.
So so if you were to come to me with that question and say, Tim, I'm using your M8 solder paste now, and I want to put conformal coating on top of it, which one should I use? These are the restrictions that I have, meaning I don't have any time for drying, so I have to have something that comes off the line dry, that it can be handled immediately. So those decisions also have a bearing on what material set are appropriate for the application. And then once you've figured that out, then you go to putting the two things together, putting them in we put them on the B24 coupon. We run them through the IPC 4090 or 8585 testing. And if everything comes above 10 to the 8th or 100 mega ohm, that we consider to be acceptable. Other companies have more strict requirements. We've encountered some frankly unreasonable test protocols. I don't know anything could pass, but what I just described is generally what is the accepted criteria. But I think like I said, the IPC is working on giving us a more formal test protocol and outcome.
Okay, thank you.
Sure. Great question. Complex issue.
All right, so we have a few more questions. So one is asking if we'll share the presentation. This will be shared as a PDF, and I believe the recording with everyone afterwards. Another question was if someone had a link enabling to view former webinar recordings. I would say I might direct you to Kelly Peretz, who might be able to share that with you. So K Peretz, yeah.
Yeah.
Put
So
put your email in the chat, Kelly.
Okay, I'll put it in the chat, and then just as a sneak preview, I'll put the link to the REL 61 webinar that we did.
Awesome, perfect. Thank you so much. And then we have a question on qualification of printing type 4 and jetting type 6 with the same flux family onto the same board. I think the general rule is that would probably be fine, but if they are different flux mediums, I would say talk to us and see if we have any insights or test it out and just make sure it works. But in general, I don't think that's an issue.
More specifically, we have if you're referring specifically to a micronic jetter, we work with Micronic on establishing, so we have a defined micronic jetting paste, recognizing that it may be combined with one of our common no cleans. We test it with our H10 and we test it with our M8 to make sure that they're compatible. J standard 001 states that you need evidence of compatibility between all the fluxes that are used on your assembly. We can provide that information. If you are using vendor A and vendor B, that's on you, meaning again, you have to generate that data if you want to be compliant to the J standard compatibility test.
All right, I think we're about at the end of our time. If anyone else has any more questions, definitely feel free to reach out to us and we're always happy to help. And again, thank you so much for coming and spending an hour with us and learning about finer solder pastes.
Great presentation. Thank you.
Great job. Thank you.
Thank you.
Thanks, Gail.
Thank you.